In this video, we will introduce another integration technique, trigonometric substitution. Trigonometric substitution is used when you see something like this, a square root of something square minus or plus another thing square. You will not see trig functions inside, but instead it's a square root of something plus or minus another square. First, gonna talk about how do we decide which substitution to use. Although I gave you a table, but I don't really want you to memorize it. We'll talk about why do we choose each of the substitution and why do we need each of the conditions here. First, let's start with square root of a squared minus x squared. The main reason we use this substitution, x equals to a times sine of theta, is because we know one of the identity, that is 1 minus sine theta squared equals to cosine theta. That is, if we do the substitution a sine theta, we would have square root of a squared minus a squared times sine theta squared, and we can factor out a squared, and then we would be left with 1 minus sine theta squared. And because of the identity, we can change this to cosine theta squared. Then instead of two terms minus each other, we would have one term, and the square root and square, we would have a absolute value of a cosine theta. And here comes the reason why we need this restriction, because well, here recall that square root of x squared equals to absolute value of x, which means here we would have absolute value, but of course we want to get rid of this absolute value. And recall Castro rule, that's what you learned in high school, or what I usually say is all students take calculus. So all students take calculus, using this to decide the sign of your trigonometric functions. From this you can see that cosine x is positive in this region. That is, cosine x is positive when my theta is in between negative pi over 2 to pi over 2. This is by Castro or all students take calculus. We know that it's positive here, which means if my theta is in this region, then my absolute value of cosine theta equals to cosine theta, which means I can get rid of the absolute value simple. Of course, a depends on if it's positive or negative. I'm gonna leave it like this at the moment, and cosine theta. And in this case, you would know what a is. It's gonna be a real number, so you would know what this is. And cosine theta is easy to integrate. That is the reason we choose this restriction on my theta, such that my cosine theta is positive. Of course, this identity, I can change it a little bit and use 1 minus cosine theta squared instead, and it works exactly the same way. So the first one, there is a different way. Of course, you don't have to set it up as a sine theta, because I also know that 1 minus cosine theta squared is sine theta squared, which means, of course, you can set my x as a times cosine theta. And in that case, if I set it up like this, this will change, or the sign will change to cosine, so we can do it again. Then in this case, my a squared minus x squared becomes square root of a squared minus a squared cosine theta squared, which becomes square root of a squared times 1 minus cosine theta squared. And in this case, I can change the 1 minus cosine theta squared as sine theta squared, so it becomes a squared sine theta squared. And of course, that's the absolute value of a sine theta. But in this case, if you choose this substitution, then we need to pick the region where my sine theta is positive. So again, draw the graph. All students take calculus. You'll see that sine is positive right here. So if you choose to use this substitution, then here the restriction you need to add that my theta has to be in between 0 to pi. To summarize this, how do we know we need to use which substitution for this one? You just think about, well, think about a as 1. So think about well, which trig identity would give you 1 minus x squared equals to something we know, a term we know. And from that, you'll see that, well, if I let this x be either sine x, means sine theta, or cosine theta would work, and the restriction depends on which one you set it as, and using Castro you can figure it out. That's the first one, and using the same idea we can decide for the second one. So for example, I have square root of a squared plus x squared, and think about what I said from before. I'm thinking, consider this as 1 again, so 1 plus x squared need to equal to a single term that we know using trig identity. So this reminds me of that 1 plus tangent x squared equals to secant x squared, which means, well, my x, maybe I need to set it as tangent x. And because I have this a, I need to factor it out later, which means, well, my x, maybe I need to set it up as a tangent x. I mean, a tangent theta, sorry. And again, this theta restriction, I don't know yet. If you don't want to memorize, then I don't know yet. I'm gonna figure it out later. And you can always do that. You can always do later parts first and add the restriction later. We know what to do with it. So we can try it. Then a squared plus x squared becomes square root of a squared plus a squared times tangent theta squared. Factor out a squared. 1 plus tangent theta squared, which is square root of a squared times secant theta squared, which becomes the absolute value of a secant theta. Well, here again, let's think about where is my secant theta positive. So all students take calculus. Here, of course, it's gonna be positive. Secant theta is 1 over, let me write it down. So secant theta, we know that it's 1 over cosine theta. So if cosine theta is positive, then secant theta should be positive as well. So this secant theta is positive if cosine theta is positive. So we're looking for this region again, all and C cosine. However, unlike what we have from before, which shows this whole region, I'm gonna remove this and this. So I'm gonna remove negative pi over 2 and pi over 2 because I cannot have cosine theta be 0. So before, here I can have cosine theta being 0, but here I cannot do that because cosine theta is in the denominator. So in this case, I need to choose theta be in this region but remove the boundaries. So it's gonna be round bracket negative pi over 2 to pi over 2. And if I have that, then I can remove the absolute value of sine. So I should add it here as well. Sine theta if theta is in that region, and here this is gonna be absolute value of a times secant theta because my theta is in this region and it's positive. And again, we know how to evaluate this integral if this is an integrand. Similarly for here. So that's the second one, and you can see that it's exactly what's written in the table. We set x as a tangent theta, and I want my theta to be in this region because that's when my secant theta is positive. Similarly, we can work on the last one, that's square root of x squared minus a squared. So square root of x squared minus a squared. Again, you can think of this as 1, and I need x squared minus 1 equals to a single term, and we're using trig identity again. So we know that secant x squared minus 1 equals to tangent x squared, right? Which means, well, my x is probably gonna be a, again because we have a instead of 1. So, and I need to factor a squared. So let's set x as a secant theta. Then, exactly as before, then my x squared minus a squared becomes a squared secant theta squared minus a squared. Again, factor out your a squared. I have a squared times secant theta squared minus 1, which is a squared tangent theta squared, and that's gonna be absolute value of a tangent theta. Now, using Castor rule again, we need to figure out where is my tangent positive. So all students take calculus. You see that my tangent is positive at all and t, right? So it means either here or here would work. You can pick any one of them. That's exactly what's written here. You can pick either here or here. Just remember that you need to remove the equal sign here, because my tangent cannot is undefined there. So again, let's write it down. So my theta could be between 0 to power 2. It's undefined at power 2. Tangent theta is undefined at power 2. Union, because you can pick the other one, union pi to okay, so it's exactly like here, because my tangent is positive here. And in that case, I can get rid of the absolute value symbol again, so I have absolute value of a times tangent theta, and we know how to integrate this, so our life will be easier if we do the substitution like this. A few other comments that I want to make. One is my x here does not need to be x, so you can consider this x as any other terms that has a x there. So it could, the coefficient doesn't have to be 1, for example. That's what I meant. So you can consider it as a square minus heart square, where you set the whole heart as a sine theta. So this heart could be x, could be 2x, could be pi x, or something. Just consider the whole thing as a unit and set the whole thing using your substitution rule. It doesn't have to be just x itself. That's one of the comments that I want to mention. The second comment that I want to mention is, because we're using substitution, if it's a definite integral, you need to change the boundaries, because now you have an integral of theta instead of x. If it's, so let's write it down. If definite integral, then we need to change the boundaries or limits. Okay, because my new integral is in terms of theta instead of x, and of course you should find your dx as well. So just like how you do substitution, after you find x, you should have, well, dx is what, dx